Okay, so I noticed that in Katrina's sessions, she has a practice problem sheet that I think Tuesday and Thursday have access to, but Monday, Wednesday, and Friday don't. Like, it's not even on our Canvas page, but like with Katrina, she like goes in and like has access to it. It's not present for us.
Okay, so let me go ahead and ask her like right now about it, because someone did tell me that there was like a practice test or something that Tuesday and Thursday had, but Dr. West said there wasn't anything like that, so I just asked her about the practice problems, and I will let you guys know.
Okay, thank you. I've heard that from other people as well and have seen it, so I just wasn't sure.
Yeah, I got you. And if anything, I'll just have her send it to me as well, just so I can then send it out to you guys. So today we are going to do chapter 12. Last week we ended off starting reduction reactions, and we basically just talked about our reducing agents. So we had NABH4 and LiAlH4. We knew that NABH4 was weak because it only reacts with group 1, and LiAlH4 is strong, which means it reacts with both groups. And then we had DIBA, which is kind of weird. It's in the middle. I like to think of it as a weak, strong reagent because it only works with carboxylic acids and derivatives, but it stops at the aldehyde. And then just to reiterate, in case you guys weren't here or you forgot, we count carboxylic acids and the derivatives in a separate group, and ketones and aldehydes are in their own group. And we call ketones and aldehydes group 1 because they're more reactive. And then we call the carboxylic acid derivatives group 2 because they are less reactive. So that's pretty much a recap of last week. Any questions or anything before we move on to reaction mechanisms? Someone asked, like, what exactly a carboxylic acid derivative is. It's basically anything that's a carbonyl with an electronegative atom here. So yeah, carboxylic acids, esters, amides, all that kind of stuff. And we'll learn more about that in the next chapter. Cool. So, as we mentioned, we're going to kind of treat group 1 and 2 as if they were separate things. So right now we're going to do group 1, which again is aldehydes and ketones. And can someone remind me? Or I don't think we actually covered that. So let's do that first and then we'll answer those questions. So what is our reducing agent here? It's written there, but I want you guys to tell me in the chat. And I'll repeat that in case that sounded weird. So in the first reaction with the aldehyde, what is the reducing agent? Yes, okay, so NABH4. But then what is the reducing species? And yes, they're actually different. Okay, cool. I'm getting a couple different answers. And it's kind of tricky, but our reducing agent is NABH4. I'll highlight that. But then our reducing species is actually just H-. And that's important because sometimes he'll ask you, like he'll give you a reaction and he'll say which one was the reducing species versus which one is the reducing agent. Just know NABH4 is the agent, the reducing species is H-. And the reason H- is important and it's kind of separate is because that is what will do the attacking. I'll actually draw it this way just to be prettier. So the nucleophile is H minus, and when it attacks the carbonyl, the electrons are going to go up to the oxygen. So we are going to get negative charge on the oxygen. And now we have an extra hydrogen bonded to this carbon. And now in solution, we have H3O plus. So what do you guys think the next step in this mechanism will be? Protonation, exactly. So this oxygen will now steal one of these hydrogens. And the only thing that will change is now we have an alcohol. And someone please remind me, is this a primary, secondary, or tertiary alcohol? Cool, everyone said primary, and that is absolutely correct. And that is because this carbon is only attached to one other carbon. Yay. So in summary, we can say that when reacted with a reducing agent, aldehydes will form primary alcohols. And that's pretty much always the rule. When we do the same exact reaction with a ketone, again, tell me what is our reducing agent? NABH4, perfect. And then what is our reducing species? H minus. And what is H minus going to act as? A nucleophile, perfect. Okay, cool. So we attack, electrons go up. We get a negative charge on that oxygen. So what is our next step going to be? Protonation, perfect. So this oxygen will steal a hydrogen. And also, I don't know if you guys can hear the noise that's going on in the background. I have no idea what it is, but I apologize. Okay, so is this primary, secondary, or tertiary now? Secondary, wow, you guys are so stellar. I love it. And again, that is because the carbon is attached to two other carbons. And so now we can say in summary, when reacted with a reducing agent, a ketone will form a secondary alcohol. Ta-da! And then someone said, OMG, I'm learning. That makes me so happy. Any questions on what we just did? If not, congrats. You just did a real whole reaction mechanism. Yay. So proud of you. You guys are killing it. Woo. It's great. And someone asked, what is the NABH for? And it is essentially supplying the H minus. That's why it's your reducing agent. And then the H minus is your nucleophile. Also, I don't know if you guys noticed, but when I uploaded the videos from the session to the YouTube or whatever, I covered up the chat box and the participant list just for privacy reasons, because I don't want people to feel like their messages and everything that they sent privately or whatever are on display anywhere. So I covered them up, and for that reason, I'm gonna read all the questions before I answer them, just so people who watch them later aren't super confused. So yeah, that's why I read them out loud. I won't read your name or anything, just again for privacy reasons. And cool, now we're going to move on to group 2, which are the more fun ones in my opinion. And let's just go ahead and start with a question. That's a review from last week. Why would we use LiAlH4 instead of NABH4? Yep, and pretty much everyone in the chat said it because it's stronger. And the reason that we need a stronger reducing agent is because we have a less reactive electrophile. And so what is our reducing species when we use LiAlH4? What do you guys think? Yep, it is still H-. For a reduction, it's always going to be H- no matter what the reagent is. So again, it comes here and attacks, and we kick these electrons up. And we get a negatively charged oxygen again. So, what do you think we are going to do next? And while I wait for an answer about that, I'm just going to reiterate because someone asked why. If you unmuted your mic, give me 1 second to explain, and then you can ask your question. So the reason we're using LiAlH4 now is because of electronic and steric effects. This is going to be much less active than our ketone or aldehyde. So because of that, we have to use a stronger reducing agent in order to make our reaction proceed. And then, did someone have a question or a comment or anything?
Oh no, I was just saying, next step, wouldn't it be pronation?
That's a great idea, and that's why I want to kind of pause and give another concept to you guys. So, what is the hybridization of this carbon right here?
Is it SP?
Close. Okay. What about this carbon right here?
SP?
Yeah, so triple bond would be SP. So then what is a double bond going to be?
This one's SP2.
SP2. And then what about a single bond like this?
SP3?
SP3, exactly. So which one of these hybridizations do you guys think is the most stable?
SP2?
No.
Or let's, for the sake of this example, let's not even count SP. So let's get rid of that. Between SP2 and SP3, what do you guys think?
SP3, because SP2 has more like steric hindrance.
That's a good point. Steric hindrance does come into it, but because of the way our orbitals are laid out and where our electrons are actually going to be, SP2 ends up being more stable, which is kind of counterintuitive a little bit because you think the double bond kind of messes things up. But because of the way everything becomes conjugated in the double bond, that one becomes more stable. That's a weird explanation for it, so I'll just repeat it one more time. So because of the way our orbitals will be facing in the case of the double bond, our electrons will be in more stable locations, and so the SP2 hybridization will be more stable.
Does conjugation has something to do about it?
Yeah, so that goes into hyperconjugation, but I took it back kind of because you guys don't have to know necessarily. But in case you're interested in it, yes, look up hyperconjugation effects, and they're really, really interesting. So with that being said, I'll highlight that in the corner as a little like off to the side tidbit of information. Now that you know that, what can we do with this instead of protonation?
So the OH will form in different oxygen, right? So the electron can switch. Did I say something wrong?
I think I understood you correctly. So you said instead of protonating, doing something else with these electrons?
The electron will move.
Yes.
Like
Yeah, you're right. And then someone else also said in the chat, these will essentially come down and reform the double bond and kick off our leaving group. So now we have this. So what functional group is this?
Aldehyde.
Aldehyde. Super. Okay. So do you guys think we're done?
No, because we have the H3.
What was that? Sorry.
We have H3O still, right?
Yes, but we actually, before we can use the H3O, have something else to do. And then someone did say it in the chat. So we do have more of our reducing agent. So we're going to go ahead and actually attack again and do the reaction one more time.
Do we need lithium aluminum hydrate like excess or something, or not necessarily?
No.
Or are we gonna like protonate it?
So lithium aluminum hydride is such a strong reducing agent that it can just work multiple times. You don't necessarily need extra. But that's a really good question. So now at this point, we're finally going to use our H3O plus to do what?
Oh, protonate the oxygen.
Protonate. Awesome. So we create an alcohol, or we form an alcohol. Create sounds weird. And is it primary, secondary, or tertiary?
Right.
Be tertiary.
So if we have one carbon here, how many other carbons is it attached to?
One, six.
Yes, exactly.
Yeah, that's okay.
So when reduced with a reducing agent, or when reacted with a reducing agent, we are going to form primary alcohols. And the fun thing we're actually going to do, this is a little sneak peek into chapter, I think, 16, where we talk about this lovely molecule. Does anyone have any idea what this is called? If not, that's totally fine. But if you do, you get extra credit in my heart. Okay, I got a couple guesses. This is actually called a... Oh, it'd be nice if I had my pen. Lactone. Has anyone heard of beta-lactones or beta-lactams? Have to do with antibiotics and stuff? Yeah, most people have. Cool. So we're going to learn about that later on. Just a sneak peek. So in a couple chapters from now, when I ask you what this is, remember it's a lactone. And essentially, it's just a cyclic ester. So we can do the exact same reaction in the ring system. So we're going to attack right here, or I'll draw a better arrow. We're going to attack right here, kick up those electrons.
Excuse me, are we gonna end up like cleaving the ketone?
Yes, we are. So what do you guys think the next step would be after what we did in the above reaction? Yes, so someone said double bond reforms and cleaves the ring. So you're absolutely correct. This pair of electrons goes down, reforms a double bond, and breaks this bond right here, opening the ring up this way. And I hope by now you guys already know what I'm going to say. We're going to count our carbons. So this will be carbon 1, 2, 3, 4, 5. So we draw a 5 carbon chain. 1, 2, 3, 4, 5. Sorry, I get really perfect, whatever. I don't know what the word is. Yes, so 1, 2, 3, 4, 5. On carbon 5, what should I draw?
The oxygen.
The oxygen, is it going to have a charge?
Is it gonna be a double?
Not yet. Or this one actually won't be a double bond because it's just going to be negative for now. And we don't have space to create a double bond because we have 2 hydrogens here and we can't get rid of them. So it's just going to stay an O- for now. And on the other side, we have an aldehyde. So you could actually do this one of 2 ways, whichever way makes sense to you. We know that we have to protonate as negative charge, right? But we also know that we have more H- in solution, and it's going to attack this carbonyl again. So what I like to do just for simplicity is do that attack one more time and then protonate everything at the end. But you could have also protonated and then continued with the reaction. It doesn't matter. So I'm just going to duplicate because I'm lazy. And so now the oxygen has a negative charge again. And we added another H. At this point, what are we going to do? I kind of already gave away the answer.
You create this time a double bond.
So that's a good guess. But do we have any way to take off these hydrogens to create a double bond?
Not negative charge.
Elimination.
I mean, theoretically we could, but we don't have anything to do with elimination, so all we really can do is protonate.
Mm-hmm.
And so that's what we're going to do.
Are we like a dial?
Yes. Okay. So we protonate twice on both sides, and we make 1 primary alcohol and 1 primary alcohol. So what we set up here is still true. If the ester is reduced, it's going to make a primary alcohol. But what I want you guys to take note of is that we could have gotten either a secondary or a tertiary alcohol here, depending on our substituents. So the alcohol that we care about is this one right here. And the reason for that is it's the one that was formed from this oxygen, not this one. Oh, yes, and the person is unmuted. Please mute. Okay, cool. Thank you. Any questions on what we just did? I know it's kind of confusing because it's a ring and everything. But any questions?
So we don't take into account the other alcohol at all?
I mean, you do kind of have to know what's formed and like what's happening, but if he asks you like what kind of alcohol do you form, he kind of wants you to focus on this one. That's the more important one.
Okay, and it can all, you said it could be tertiary or secondary, right?
This second one, yes. So if you had a substituent here, you could have gotten a secondary or tertiary. But this one over here will always be primary.
Okay, thank you.
You're welcome. Sweet. Okay, so I am actually going to leave this reaction for you guys to practice on your own. And the reason for that is it's actually the same exact mechanism as the ester, but now instead of an OR group, you have an OH group. And so, spoiler alert, if you react a carboxylic acid with a reducing agent, you're going to form a primary alcohol. So, like I said, all the group 2 reactions will be exactly the same. So, in summary, just to recap, if you react an aldehyde with a reducing agent, you get a primary alcohol. If you reduce a ketone with a reducing agent, you get a secondary alcohol. In group 2, no matter what carboxylic acid derivative you reduce, you will get a primary alcohol. If you reduce a lactone, which is a cyclic ester, excuse me, you are going to again get one primary alcohol and then another alcohol that will vary depending on your substituents. Any questions so far? Sweet. Okay, so now that I give you the long way to do everything, I want to kind of show you the shortcut of how I just see a molecule and can already tell what the product is. So we already did the lactone one. I'm not going to redraw that for you guys, but I will give you another example. So let's say we had a methyl substituent right here. Well, I already know that I'm going to have 2 hydrogens attacking because we have this leaving group, and I know that we're going to open that way, right? So let me, 1, 2, 3, 4, 5. Again, we have a 5-membered, a 5-carbon chain. 1, 2, 3, 4.
So we're gonna need a strong nucleophile, like a hydrogen delivery reagent.
Yes. But it doesn't really matter what we're using because I just want you guys to be able to see starting material, final product for this case. But you're totally correct. So on carbon 5, we have a methyl and an oxygen. And we know that's going to get protonated. And then we have our oxygen that was part of the carbonyl. That gets protonated. And we also have to add those 2 hydrogens from the reduction. And we knew that we were adding 2 hydrogens because we always do at least 1 for a reduction. But since we had a leaving group, we're going to add 2. And this is what our final product should look like. That was kind of fast. Any questions about how I got this?
How did you get the alcohol on the left? Like, how did you know to put a methyl there?
Okay, great question. So this, So this is carbon number 5. And we knew that carbon number 5 has the O, and it also has a methyl. So we have this methyl, we have the O, and then we know that the oxygen would have a negative charge, and it has to get protonated. So that's why we end up with an alcohol. And then if you still kind of don't see it, I suggest going back up here, because over here we saw that when we attacked excuse me. When we attacked right here, we had to break open the chain to reform the double bond. So this oxygen was left over with a negative charge, and then it had to be protonated to get our final product. And so we're doing the exact same thing over here, except we have an extra methyl.
Can I ask you a question?
Yes.
Why is there two hydrogens for carbon number 1 when did you deprotonate it or protonate it twice?
Yes. So we're not going to say protonated only because it's not technically the correct word. So use reduced. But other than that, you're totally correct. So we're going to reduce this carbon twice because the first time we attack a hydrogen, we reform the double bond. And when we reform the double bond, we can attack it one more time to form our...
Oh, okay. I'm sorry, I remember.
No, that's okay. Don't be sorry. I love questions.
I have one more question.
Yes, go for it.
So, do we only need to know the products formed, or we need to know like the mechanism?
So for reduction, so for oxidation, you only need to know products. For reductions, it's helpful if you know the general mechanism, but for the exam, you're not going to have to draw out a mechanism. So at the end of the day, you just want to be able to give me the products, but it's useful for you to understand the mechanism.
So there won't be like a question where there's like arrows and it says like...
There has never been in the past, but I know that you guys were telling me there were some mechanism questions on exam 1. So I'm going to ask him during our meeting just to double check and confirm that for you guys. But from my experience, no, there's never any mechanism questions.
Okay, thank you.
You are very welcome. Alrighty, so doing the same kind of quick way that we did before, we're going to do this. And how many protons are we going to add in this reduction? What do you guys think?
Only one?
Just one, exactly. And the reason for that is we don't have any leaving groups. And since this is a ketone, what kind of alcohol are we going to make? Primary, secondary, or tertiary?
Secondary?
Secondary, awesome. And then someone did point out this is a group 1. You're totally correct. And there we go. We make our secondary alcohol. And of course, we have to add that hydrogen in there. Next up, if I move to the other side.
I have a question.
Yeah, go ahead.
Okay, so for like on the exam, should we make sure that the H is there and never assume that like it's an applied hydrogen? So say if like that he had this answer and then another one just like that, but without the H.
So you mean like just this?
Yeah, like even though it's kind of like we know it's there, but should we always choose the answer that shows that it's there?
That's a great question. Because sometimes it's kind of hard to know what exactly is an implicit hydrogen versus what has to be drawn. In this case, this is implicit. So he doesn't have to draw it. You just know it's there because there's no charges or anything here.
I guess this answer goes on the exam. So if on the multiple choice he shows both these answers, the one with the hydrogen would be the better choice to pick.
If he gave you both, yes, but he wouldn't do that because these are exactly the same.
Okay, thank you.
One thing he will do, though, is he'll give you, like...
A and B. He can do that.
I did not hear what you said.
He can put them as two answers, and like A and B, both choice would be correct. So that would be answer choice E.
Yeah,
You know?
that's true. but I still don't think he would, just because they're like kind of the same. But the more important concept there, I guess, would be watch out for reagents like this, where it's the same reagent as before, but he replaced the hydrogen with a deuterium. And now that is important because instead of having H- as our nucleophile, we have D-, which means that the answer will look like that. And more often than not, he will give you deuterium so that you can see it drawn out here, because deuterium is not implicit, it has to be drawn out, so that he knows that you know that you're supposed to replace this hydrogen here. Does that kind of make sense? That was a really good question about the hydrogen.
Yes, thank you.
You're
Go with
welcome.
the oxygen.
I'm sorry, can you repeat that, please?
Would the deuterium ever go with the oxygen, like in the OH?
That is a great question. So if he gave you, let me just draw it out on the side.
Excuse me, I don't think that will be a functional group, right? You're right. It's in hydroxy OH, not OD.
Yes, but deuterium is just an isotope of hydrogen, so it's essentially the same thing. So let's say he gave you NABD4, just like I wrote before. If he gives you H3O+, you would make this, because then the acid has a hydrogen. But if he gave you NABD4 D3O+, which he 100% can, then in that case you would make that answer choice. Again, really awesome question. I don't know if you guys can see the whole thing. Does that answer your question?
Yes, it does. Thank you.
You are very welcome. I love all of these amazing questions. Also, it is 1:50, and this is technically the end of the SI session, but since I was 10 minutes late, I will continue for another 10 minutes, and then it will be posted online for you guys. So if you have to go, I totally get it. Goodbye. Have a wonderful Monday. If you want to stay, cool. We're just going to finish up reductions. It shouldn't take too much longer. If you are going to go, though, and you have questions, I'll give you a couple seconds to ask.
Remember to send the attendance.
Yeah, I'm going to send that right now. I'm so sorry. I forgot. It's been a rough Monday. It'd be really cool if it would load. I will continue talking because I don't want to waste your guys' time. So for these two examples, I want you guys to think about it for a second and try to draw it out yourself. I'll give you like a minute. I'm not going to put you guys into groups because that'll take too long. But I want you to try to draw these two out by yourselves. And again, I'll give you 1 minute, and then I'll give you guys the final product.
Excuse me, are you still there?
Yes, what's up?
I wanted to ask you on the last one, and since we got Ester, isn't it gonna cleave and we're gonna end up with two products, or what's gonna happen there?
That's a great question. So I want you guys to think about
Oh,
the two products that would be formed. So yes, you're right. There would be two products. But I want you guys to think about it before I give you the answer. And I just sent out the attendance link. Thank you to the people who reminded me. You're the real ones. One thing you'll notice about me is that every time I give you guys like 1 minute or 5 minutes or whatever, I literally never keep track. So I'm going to wait like 10 more seconds and then we'll go into it. I think that was 10 seconds. I realize I haven't stopped talking during this 1 minute, but that's okay. That's what you guys are here for, right? So, how many hydrogens are we going to add for this one?
you just need one.
Just one, exactly. So, we keep the benzene exactly the same. We're not going to touch it. But instead, we will protonate and add a hydrogen here. And so, primary, secondary, or tertiary. What is this?
That's gonna be a second.
Yep. Cool. Any questions on that one? Goody. Okay. So, since we have a leaving group, how many hydrogens are we going to add here?
Uh,
2. Yes. Cool. And so on this side, we add 2 hydrogens and we make an OH. And as someone mentioned, we are going to have another product over here on the side. We keep the benzene ring exactly the same. We're just going to protonate this oxygen. And so we get a benzyl alcohol. Does anyone remember what the name for this is?
it said phenol or phenyl? Phenol.
Phenol, yes. I'm so proud of you guys. You're doing amazing. And so is this a primary, secondary, or a tertiary alcohol? Primary. And then someone asked a question, but I didn't see it, so I'm gonna scroll back. And okay, so the person asked, so we get 2 separate structures? Yes, but you only care about this one. So if he asks you for the product, this is the one he wants. This will just be a byproduct. So whatever the leaving group was, will just be a byproduct. It's not going to be your main product. We are not usually going to care about it. I just drew it out so you guys know that it doesn't just disappear into space. It'll still be there. Any questions about these 4 that we did? Okay, so one person asked why were 2 hydrogens added, and so I'm going to give you a little kind of summary cheat sheet kind of thing. So in a reduction, you always add at least 1 hydrogen. And then for every leaving group you have, add 1 more hydrogen. So if you have 1 leaving group, you add 2 hydrogens. If you were to have 2 leaving groups, you would add 3 hydrogens, but we don't really do that in this class. So that's kind of the summary, how I remember it. And then someone else asked, why isn't the benzene ring here considered a leaving group? And that is because something will only be considered a leaving group if it's not a carbon-carbon bond. The only time we have a carbon-carbon bond breaking is way in chapter 18, and it'll be a very specific case. So this is different than this because we have an oxygen in between here. And then someone had asked the same question, But it's a great question. I totally understand why it's a little bit confusing. But cool. All right, the last thing I want to cover, I don't know why I wrote 192 on here. Whatever. Not important. So I'm actually going to let you guys do this one on your own as a kind of practice for drawing out condensed formulas. So the actual answer itself just has to do with converting this ketone to an alcohol, and then this functional group, you guys have to pay attention to what this is. So I want you guys to do this yourself, practice drawing it out, and then we will cover the answer next time. Yes, Kristen?
Excuse me, is it possible to use H2O with NaBH4?
Yes. So
if it wouldn't be the answer A and B then?
No. And that's the reason I want you to draw it out. It's not going to be both because you have to consider the ketone and this functional group. Does that make sense?
Like if I want to keep the CO2, if I were to use LH4, I might like convert the whole thing.
Exactly. So you have the correct idea. I will draw it out and do the whole thing on Wednesday. But yeah, I want you guys to practice drawing it out. And also, I think I'm frozen, and that is the most awkward face it could have frozen on, but that's fine. One person asked, going back to the earlier concepts, in terms of solvents and reagents, are there anything else you guys have to be aware of? And no, not really, as long as you know NaBH4, LiAlH4, and DIBA. That's all you need to know for reductions. And this is all you need to know as far as oxidations go. And remember the 4 or more oxygens rule. That will be really, really helpful. As far as like the reagents versus species thing that we talked about, for oxidation, that doesn't really matter. We're not going to differentiate things like that. For reductions, just know that whatever reagent he gives you, NaBH4, LiAlH4, or DIBA, those are all oxidizing reagents, reducing reagents. But the hydrogen, or the hydride, H-, is always going to be the reducing species, because that is a nucleophile. And you're very welcome. Let me see if there were any other questions. I don't think so. So, yeah, that's pretty much all I have for you guys today. I'll stay for like 1 more minute if anyone has any questions. But, yeah. Have an awesome Monday. See you guys on Wednesday. Bye-bye.
Actually repeat really quick just what you said, the carbons for leaving groups. I don't remember if you said between 2 carbons.
Wait, were you talking about this for the leaving group?
Yeah.
So what I was saying is that, for example, why this benzene ring was a leaving group and this one was not is because this one is directly attached to the carbonyl, and it's a carbon-carbon bond, which we're never going to break. Versus in the second example, there's an oxygen in between. So we're actually breaking a CO bond, not a CC bond. And that we can do because it's electronegative.
Gotcha.
Yay. Okay, cool. So have a nice day, everyone. Bye-bye.
Bye, thank you.
You're welcome.